In this video, we're going to discuss exactly what implicit differentiation is and how you can use two simple rules to always do it correctly. Let's jump in. First, let's talk about exactly what implicit differentiation means. The differentiation part means taking the derivative. It's just a big, complicated word for take the derivative, basically. But that begs the question, what does the implicit part mean? Implicit, and this is like the form of an equation, in implicit form, it really just means, the way I think about it, not explicit. But of course, now we need to know what explicit form means. So here's what explicit form means. Explicit form means that the y in the equation shows up in one spot on one side of the equation all by itself. If those three things happen, it is explicit form. If any of those or many of those are missing, it's implicit. So for example, you can see this one over here on the left is explicit form because y shows up in one spot on one side of the equation all by itself with nothing else going on. And then everything else on the other side is either a constant or some function of x. These on the right, these are both implicit forms. Now, these are all the same equations, by the way, but like right here, you can see that right off the bat, y is not by itself. So it's not on one side of the equation. It's mixed in with other terms, like it's mixed in with a bunch of x's, for example, and it's being squared. Those two facts make it not explicit, therefore it's implicit. We're defining the function with y kind of wrapped implicitly into the equation. It's not completely separate, or it's not clear what y is by the equation. This format would also, even though it's the same, it again describes the same equation, it's still not explicit form. This is also implicit. Even though y is by itself on one side of the equation, because we're squaring it, it's not the only thing on that side of the equation, if that makes sense. What we need is for just y by itself equals and nothing else, like we have over here. So this is explicit, this is implicit form. Implicit differentiation is just describing how we take the derivatives of equations like this, because we can still do it. So hopefully that makes sense. Now let's jump into some more applications. So if that's what implicit differentiation is, the next question is, how do we actually do it correctly? And the answer is these two rules. Basically, all you do is take the derivative normally. If by pretending that y is x, you just do the same thing you would normally do if you already know your derivative rules, and then multiply by dy dx. If you just follow these two rules, you will always do implicit differentiation correctly. So let's actually see how to apply these. So if we're going to try to implicitly differentiate this actual implicit equation, how do we do it? First off, we need to take the derivative of both sides, so that's always true. So regardless of which problem we're working on, we always take the derivative of both sides first, d dx on that side. And by the way, we're taking the derivative with respect to x still. It's important to be clear about that. That's good. And now the question is, how do we simplify? The easiest thing in this case is actually probably to start on the right. What is the derivative with respect to x of 4? Well, 0, because 4 is a constant, so it does not change at all when x changes. So the derivative is 0. Now on this side, I'm going to break this down into more steps than you probably need, because I think it's useful, but basically I'm just going to break it apart first off with the sum rule. So the sum rule says that if you want to take the derivative of something plus something else, you can take the derivative of each of them individually and then add them together afterwards. And then now the question is, what are these? So this one, you can see there's no x's, or sorry, there's no y's in this term, which means this part right here specifically does not need any of these implicit differentiation rules. So this would just be normal. This would just be 2x, the normal power rule. This is where we need the rules now. So if we have y squared, again, now we're trying to take the derivative with respect to x, but there's a y here. And just to be clear, if we were trying to take the derivative with respect to y of y squared, that would just be 2y. Just like the derivative of x squared with respect to x is 2x. So in other words, if the variable is the same, you just do the normal rules. So if the variable is the same, you just do the normal rules. What you need implicit differentiation for is when the variables are not the same. So here, you see the x and the y. We have a function y, and we're trying to take the derivative of it with respect to x. Y is not x, so we're basically assuming that y is a function of x, but we don't really know. And if we just assume that, then implicit differentiation applies. So how do you do it with these two rules? So rule number one is take the derivative normally as if it were x instead of y. So if this was x, we already did it over here actually. If this was x squared, what would it be? 2x. So it's just going to be 2y. To do the same thing you would have done over here, just replace it with y at the end, basically. So that's going to be 2y. And then rule number two is multiply by dy dx. And if you're curious about why we have to multiply by dy dx, I won't get into it in this video, but it's essentially the chain rule is the reason we have to do that. We're assuming that the outer function is x squared and the inner function is y as a function of x. So we take the derivative of the outside, 2x, but we evaluate it at y. And then we have to take the derivative of the inside according to the chain rule. That's the dy dx part. So implicit differentiation is really just an application of the chain rule, if that makes sense. But anyway, after we've done this, mission accomplished. So once you get to this point, you should have basically a dy dx somewhere, and that's the thing we're actually trying to solve for. That is the derivative. So what we're going to do now, and again, different problems could do things a little differently. If you have dy dx that shows up in multiple spots, you're going to want to get everything on the same side, factor out the dy dx, and then divide by the remaining term, if that makes sense. Or the remaining factor, I should say. But in this case, because dy dx only shows up in one spot, we don't need to do that. So it's a lot easier here. So I'll kind of jump to the end here. Hopefully this makes sense. Hopefully you can algebraically isolate it at this point, but you'll get dy dx equals negative x over y, because we're going to subtract 2x, and then we're going to divide by 2y. And the 2's will cancel out, and we'll be left with this. So there you go. That's the implicit derivative of this original equation with respect to x. But the question is, what does this actually mean? Remember, we just took the implicit derivative, the key word there being derivative. Because this is still a derivative, it still represents the slope of the tangent line to the curve at every single point. So for example, remember, in this case, this was actually the derivative right here. Again, you don't have to really worry about this equation. This is really just point slope form is what I'm doing here. But this right here is the derivative. At any x and y coordinate, if you plug them into this equation, it should tell you the slope. So for example, and again, I'm specifically picking points that are on this curve. I could have picked other points. I can pick points anywhere for this animation, but I'm just going to pick points specifically that I already know are on the curve. So y is 1.41, and then x equals 1.41 on the curve on this equation. And again, this is not a function, by the way, because it fails the vertical line test, but it is an equation still because it has an equal sign. So why are these points on the curve? First off, plug them in and verify. Second off, this is 1.41 is the square root of 2. So it's just the decimal version of the square root of 2. If you plug the square root of 2 for x and y into this equation, you'll get 4. That's why this is working as is. But anyway, if you plug any x and y coordinates that are on the original curve or the original equation into the derivative function, which we just found out was negative x over y, whatever number you get out of that will be the slope. So for example, if x and y are the same thing and I plug them in here, hopefully it makes sense that I get a slope of negative 1, which is what you can see right here. That is the slope of the tangent line apparently at that point. Whereas if I went over to 0, 2, well, hopefully it makes sense that if I plug it in here, I would get a slope of 0, which I do, and that's also right. And then what if I went to, maybe this might not be perfect, but what if I went to negative 1.41, positive 1.41? Well, if I plug those x and y values into this equation, hopefully it makes sense that I get a slope of positive 1, which again is also believable. We're still talking about the slope of the tangent line here. That's the most important part. So we're still talking about the derivative here, which means the slope of the tangent line to the curve at any point. The only difference here is that it is a function in general, when you take implicit derivatives, of x and y, not just x like it has been when you're taking explicit or normal derivatives that you're used to. So one question you might be wondering is, if the implicit derivative is still the derivative, just in a different form, does that mean that these two derivatives are the same? And the answer to that question is actually yes. I won't go into the full derivation here, but you can kind of work out on the left here why this is actually true. If you just take the derivative of this with the power rule, using fractional exponents, of course, and the chain rule, you can work your way down to here. But basically, what I'm claiming is that this derivative and this derivative are actually the same. They're just in a slightly different form. Now, how can that be? Well, remember, what is this y value down here? Well, from the explicit form, we already know that y is equal to the square root of 4 minus x squared. And that is actually showing up right here, if you notice. So just by basically substituting in for y what y actually equals, you could actually get it back to the explicit form. In other words, these are exactly the same. It's just that this one is expressed purely in terms of x, just like the explicit form before taking the derivative. And this one is expressed in terms of x and y, just like the implicit form before the derivative. But they're both fundamentally talking about the same thing, is the point. So there you go. And in this case, I should actually add this before we go. You can see this isn't always true, but in this case, it actually looks a lot cleaner, I think, in implicit form. It seems a lot simpler, whereas here it looks a little bit uglier. So this is like one example of why sometimes we might actually prefer implicit form. There are other reasons that also make sense, but that's definitely one of them. So there you go. Hopefully that makes sense. Now you know what implicit differentiation is, why it works, and how you can always do it right with the two rules that we covered. And if that makes sense, I will catch you next time. See ya.